Welcome to ECE 461 Control Systems, lecture number 16, Rotational Systems with Gears. Now what we're looking at in this lecture is trying to find the transfer function for a rotational system. That'd be things like when you're an ice skater, you spin your arms around, a motor is spinning, various things that spin. Now rotational systems behave just like translational systems. For each, you've got mass, spring, and friction. The difference, though, is in rotational systems, they have a slightly different symbol. The symbol for inertia is like a mass. Think of a solid iron core. It takes energy to make it spin. Once you get it spinning, it wants to keep spinning. And the symbol for rotation is J for inertia. And the variable is theta, the angle, rather than displacement. You also have friction. Again, think of it if you have like the brakes in your car. If they're rotating and apply the brakes, the difference in rotational speed is what causes the energy release, or the force, actually the torque in this case. And a spring. And a spring would be like a watch. You wind up a spring and it makes the clock spin. So again, you've got mass, spring, friction from rotational systems. Behaves just like a translational system. For example, suppose I have the following three-mass system. If I take the first mass, J1, and apply torque to it, that's going to make it rotate. It's connected to mass 2 through a spring, and connected to ground through friction, again trying to keep it from spinning. That spring then applies a torque to theta 2, inertia 2, causes it to spin, and that's connected to theta 3 through a spring. That's connected to ground. Ground is a non-rotating reference frame. To come up with the dynamics for this system, do the same thing we did with the mass spring system. Draw the circuit equivalent, and then write the node equations. So to draw the circuit equivalent, I've got three inertias. That's three inertias to ground. Again, from Einstein's theory of relativity, all inertias are relative to a non-accelerating reference frame, ground. Attached to inertia 1, I've got a torque. As the torque increases, that increases theta 1. As the current goes up, it increases voltage, theta 1, so that's consistent. I've got friction to ground, that's D1S. I've got a spring going between inertia 1 and inertia 2, there's K1. Inertia 2 has got friction to ground, and a spring going to inertia 3. And inertia 3 has got friction to ground and a spring to ground. So there's your circuit equivalent. Once you draw the circuit, it's write your node equations. And here we're going to be doing the sum of the admittances. Again, note all these are admittances, not impedances. I'll sum the admittances attached to node 1 times theta 1 minus the admittances between theta 1 and theta 2 times the admittance times K1 is equal to the current to the node, torque. At node 2, the admittances attached to the node minus the admittances between nodes 1 and 2 times theta 1 minus admittances between nodes 2 and 3 times theta 3, and I misspelled theta 3, equals the current to the node, 0. And at node 3, all the admittances attached to node 3 times theta 3 minus the admittances between nodes 3 and 2 times theta 2. So once you get the equations, then I solve for the highest derivative and throw that in matrix form. And just like a mass spring system, three inertias actually gives you a sixth order system. I've got the angle and velocity. The derivative of angle is velocity, gives you the zero identity matrix. Derivative of velocity is acceleration. That's where you get the dynamics. So plugging these in over here, I get the net system. And notice this is a spring matrix. All K's, this is a friction matrix. To check for sign errors, the diagonal should be negative, off diagonal is positive. And notice right here, I've got a sign error. That's a quick way to check for sign errors. And the diagonal should be negative, meaning if I take a spring and turn it, it should come back. The off diagonal should be positive. This tells you who you're connected to. As theta 2 increases, that should increase theta 1, not decrease it. It's a quick way to check for sign errors. And then if you want to simulate that, you can simulate how that behaves just using numerical integration. For example, here's a routine. I just draw a circle centered at x, y, radius r, and angle phi. What this does is it goes around the circle 360 degrees and then shoots across, draw a line through it. The dynamics for that last system are these dynamics. Again, noting for sign errors, at node 3, all the theta 3s are negative, everyone else is positive. At node 2, all the theta 2s are negative, everyone else is positive. At node 1, all the theta 1s are positive, everyone else is negative. Assuming the inertia is 1, friction is 1, spring is 10, I can then calculate the acceleration at any given time, integrate acceleration and get velocity, integrate velocity, get position, and then just draw your 3 balls, the 3 rotational systems, and this is what it looks like. So the torque is on the first one, that causes it to spin. As it spins, it's got a spring connected to mass 2, causing it to spin. That has a spring connected to mass 3, which causes it to spin, and this is also tied to ground, which tries to keep it from spinning. So that's kind of how the 3 rotational systems behave. Like a mass spring system, but you're dealing with rotation rather than translation. With gears, or with rotational systems, you also have gears. Gears convert one speed to another by the turn ratio. They also convert impedances. The requirement for the gear is at the interface right here, the displacement on one gear is equal to the displacement on the second gear. And you also have conservation of energy. Power in equals power out. And what that kind of looks like is the following. With gears, you've got a fixed ratio. So whatever theta 1 is, theta 2 is theta 1 divided by 5 with a minus sign. At the interface right here, notice that the 2 gears are spinning at the same speed. The displacement on the small gear is equal to the displacement on the large gear. The speed changes though, because the circumference is 2 pi r. This one's got a smaller circumference, so a given distance is a bigger angle than the large gear. And you can also have gears on top of each other. For example, if I have 3 gears, this small gear is turning the large gear, so this one moves slower. On top of the large gear is another small gear that turns to another large gear. What happens is this gear spins counterclockwise, this one spins clockwise. Every time you go through a gear, the direction changes. And the speed slows down. As I have a small gear driving a large gear, the large gear slows down. Small gear driving a large gear, this one slows down as well. And right there you can kind of notice, right when that goes through this point, the 2 speeds match. So gears are a way to change speed. It also changes the inertia, or the impedance going through the gear. For example, suppose this gear right here is really, really heavy, hard to turn. This one is small, it's really easy to turn. Energy is torque times speed. The energy over here, I've got a low speed, meaning really high torque. Over here, I've got to have the same energy. High speed, meaning really low torque. This one's easy to turn. So if you have a contest and you want to know which one do you want to spin, you think you go for the bigger one because bigger is better. Actually, if you want to have a contest, grab the smaller gear. This one will be easy to turn. That then amplifies the torque going to the large one. And that's kind of like trying to pull your boat out of the water. I've got a small winch right here. I'll turn this winch really, really fast, and slowly the boat's pulled out of the water. So a small torque right here, or force, produces a large force pulling the boat out of the water. It doesn't move very fast, but I can get a very large force by using gears. So that's kind of what gears do. They amplify torque, amplify speed, decrease speed, change impedances, all that. Essentially, gears are the mechanical equivalent of a transformer. And to see that, do a couple constraints. At this interface right here, the distance that I travel along gear 1 is equal to the distance I travel along gear 2. So d1 equals d2. For a gear, if you're sticking with radians, the distance is r times theta, where theta is in radians. Over here, d2 is r2 times theta 2. Since r2 is bigger than r1, Q2 is smaller than Q1, and it's proportional. What that means is if I go through a gear, the angle theta 1 is R2 over R1 times theta 2. Since R2 is twice as big as theta 1, this angle is twice that one. And actually it looks like it's 3 times as big. That also applies to speed. Take the derivative. If theta 1 is spinning at 1 radian per second, theta 2 will be 1/3 of that. Or conversely, if theta 2 is 1 radian per second, theta 1 will be 3 radians per second. Gears also change the impedance. The torque is force times distance. At the interface, the force on the small gear is equal to the force on the large gear. The torque is force times distance. So this has got a very small torque, small radius. This has a very large torque, large radius. So it takes a small torque on the small gear to produce a large torque on the large gear. You also get energy balance. Energy in equals energy out. The energy in the small gear is torque times distance. That is to be the energy in the large gear. Substituting, T1 is R1 over R2 times T2. Theta 1 is R2 over R1 times theta 2. Multiplied out, the R's cancel. I get T2 theta 2 equals T2 theta 2. The energy in equals energy out. Energy's got a balance. Impedance is also changed through the gear. For example, suppose I have an inertia on gear 1. What that means is torque is mass times acceleration. Torque is J1 S squared times theta 1. What does gear 2 see? Well, we can do a substitution. T2 is R1 over R2 times T1. Or T1 is R1 over R2 times T2. Theta 1 is R2 over R1 times theta 2. So now let's bring this right. I get T2 is R2 over R1 squared times ms squared times theta 2. The inertia seen at gear 2 is the inertia from gear 1, ms squared, scaled by the turn ratio, scaled by R2 over R1 squared. And I like thinking of it as it's times where you're going to divided by where you came from squared, times R2 over R1 squared. As an example, suppose I had this system. I've got inertia tied to a spring, tied to a gear. This is a small gear that spins fast, slowly spins theta 2. Attached to a spring, attached to a gear, spins fast, slowly turns theta 3, which has inertia tied to ground through a spring. Find the dynamics for that system. Again, the first step, I've got 3 inertias. Draw 3 inertias relative to ground. The second step is add in the other components. I've got a spring going to the gear. The gear is modeled as this. This is a 1:5 transformer. What that means is 1 times theta 1 equals 5 times theta 2. Or if theta 2 is 1 radian, theta 1 is 5 radians. Theta 1 equals 5 theta 2. That gets me to over here. I've got inertia. I've got a spring going to the gear and friction to ground. I now have a second gear, 1 to 5. So 1 times theta 2 is 5 times theta 3. At node 3, I've got inertia to ground and a spring to ground and friction to ground. Now the trick is pick where you want to take everything. Let's take everything left relative to the motor to node 1. When I go through the gear, I go as the turn ratio squared. So this is going to be these times 1 to 5 squared. These will go through 1 to 5 squared times 1 to 5 squared. So these get multiplied by 1 over 25, 0.04. These get multiplied by 1 over 25 squared, 0.0016. Now I can write the node equations for the net system without the gears. And note, I've got a prime on these. That's not actually theta 2. That's not actually theta 3. These are scalars, scaled multiples. They're scaled by the turn ratio. And now I can write the node equations. I've got 3 nodes. At node 1, it's the sum of the admittances attached to the node, times theta 1, minus the admittances between nodes, times theta 2, is the current to the node. At node 2, it's the admittances attached to the node, times theta 2 minus the admittances between nodes 1 and 2 times theta 1 minus the admittances between 2 and 3 times theta 3, and likewise for node 3. So there you've got the dynamics relative to the source. Again, what that's kind of useful is gears are used in robotics. If this is the motor over here and the robot arm, if I have a 300-to-1 gear reduction, then the load relative to the arm, as seen by the motor, is scaled by the turn ratio squared. So the arm, whatever you're picking up, is scaled by 1/300 squared. So the motor, the gear basically makes the outside world irrelevant relative to the motor. All the motor really cares about is if I can control myself, control the motor's angle, I can control the tip position of a robot through the gear. So really robot control is just can I control a DC servo motor. So speaking of that, DC servo motors, there's a couple different types of motors. If you want to control a robot arm or a BattleBot or an RC car, I need a motor. And there's a couple different types. We're going to be talking about DC servo motors. DC servo motors are really nice for control systems. For these motors, current is torque. So if I have a mass spring system, I want to push a cart around or rotate a rotational system, the current is what does that for a motor, for DC servo motor. Speed is voltage, sort of. Really the current is what you care about, that's the torque. The motors are easy to model, easy to operate, easy to control. There's a lot of pluses for the DC motors. There's a minus for them. For example, it's about 2 horsepower, 1.8 horsepower DC motor is about 28 inches tall, 43 pounds, 4-inch diameter, costs $2,400 new. You can get them used on eBay for $1,500, but new ones $2,400. They're really big, really expensive, really inefficient, easy to use though. In converse, the AC synchronous motor, that's a quadcopter motor or RC car motors. These have 3 leads. This is actually a 3-phase AC motor. If I'm willing to use a 3-phase AC motor, the same power becomes the size of a D-size battery, about 9 ounces, 2 inches by 1.3 inch diameter, costs $26 new, $43 including the driver. The driver over here is a couple of $100 more as well, and about the same size. That's the fun thing about being an engineer. I now have 1 horsepower in the size of a D-size battery. What do you do with it? What you can do is you can build RC cars, you can build quadcopters, you can probably start getting into exoskeletons for robotics, stuff like that. These are a lot harder to control because for the AC motors, frequency is speed and lead angle is torque. So these are a little bit trickier. If you can figure them out, I can go from $2,500 and 43 pounds down to half a pound and $26. That's part of the reason that the technology is switching towards the AC synchronous motors. But we're going to be sticking with the DC motors. They work a little bit nicer for control systems, at least for this class. And a little bit of background on how the DC motors are built. I've got a permanent magnet on the stator, the outside side. On the inside, I've got a magnet, and here are these little brushes in here. These are all electromagnets. As I apply current to it, that provides magnetic field that's attracted to the magnets. If I just had a single one, I would need to apply an AC signal to get the motor to spin. These armature, these brushes, rectify the signal. So I've got a sine wave. If I just take off the peak of a sine wave, I get a torque. Then as it rotates, I pick off the next peak, and it gets a large torque going to the magnet. As it starts to rotate, I then shut that one off, grab the next peak. This gives you an almost constant torque for constant current. The cost, however, is I actually have, from this figure, looks like about a dozen motors in one. Only one of them is energized at any given time. All the other windings are basically wasted. So there's extra weight, extra cost. Plus they lose efficiency. When I take the coil and disconnect it, I've got energy in the inductance as 1/2 Li squared. As I disconnect it, the energy gets dumped to ground. That causes a spark. That jams the radio frequencies, gets the FCC upset. To keep the FCC happy, I have to have this big metal case around the DC motors. All that adds cost, weight, inefficiency. Get rid of that, go with the AC motor. I can make the motors much smaller. But that's how DC motors are built. To model a DC motor, the modeling looks like this. In the armature, I have an electromagnet. The magnet has inherently resistance and inductance. Plus, motors and generators are the same thing. As I spin the motor, that produces a voltage. The voltage is proportional to speed, and the voltage constant is called kT. As I apply current, the current produces a magnetic field. That magnetic field produces a torque. Torque is proportional to current, and that torque spins the motor. The motor has rotational inertia and friction. So that's the electrical model for a motor. If you use metric systems, then kT equals kT. It turns out Newton meters per amp is equal to volts per radian per second. If you work out the units, MKS, they actually are the one and the same. So if I want to find kT, whichever one's more convenient, I can spin the motor and see how much voltage it produces. That measures the volts per radian per second. I can apply current and see how much torque it produces. That gives me Newton meters per amp. They're one and the same. So anyway, that's the model for a motor. If I come up with a transfer function, write the equation on the left, I get VA is equal to this voltage, RA plus LAS times IA, plus KT times the speed. That's one equation. The second equation is the torque, KTIA, is equal to JS squared plus DS times theta. Two equations, two unknowns, substitute, solve, I get this. This is the transfer function for motor to voltage. In terms of speed, here's the transfer function relative to speed. And if you have a motor that you buy off eBay, I can figure out what the transfer function is. For example, here is an Electrocraft RDM 103 motor. If you look at the data sheets, it gives you the torque constant, Newton meters per amp. That's nice. The terminal resistance, that's a parameter. Armature inductance, that's a parameter. I actually have 5 parameters I need to find. I need to find the torque constant, resistance, inductance, inertia, and friction. The damping constant is your friction in English units, UG. Torque constant is in English units, UG. And those don't really help. So to find KT, I can take that 13.7 ounce inches per amp, convert to metric. It's 0.0967 Newton meters per amp. It's also 0.0967 volts per radian per second. The friction, I've got 0.25 ounce inches per kilo RPM. Convert to metric, it's 1.68 times 10 to the minus 5 Newton meters per radian per second. And the inertia, wherever you are, there you are, 0.08 ounce inches per second squared. Convert to metric, 5.76 times 10 to the minus 6 kilogram meters per second squared. I can now plug that in and get the transfer function. What this tells me is the DC gain is 10.31. So 1 volt in makes it spin 10.31 radians per second. More realistically, 12 volts in makes it spin at 123 radians per second. The dominant pole has a real part of minus 196. That means under no load, it takes about 20 milliseconds to get up to speed. And this is complex. There's also about 35% overshoot in the motor. And this kind of seems weird. Why would they build a motor with overshoot? Well, motors are designed to connect to a load. When I connect to inertia to it, that changes J, changes the transfer function, and I no longer have overshoot. As an example, suppose I wanted to use that motor to build a BattleBot. Wheels are actually transformers. A wheel converts rotation to translation, and the relationship is x equals r times theta. So 1 times x is r times theta. That's just like a gear, where I've got theta 1 is 5 theta 2. This is a gear where the turn ratio is 1 to r. Input is translation, output is rotation. If I take that same motor, connect to a BattleBot that weighs 2 kilograms, and the wheel has a radius of 1.5 centimeters, I get this. Same motor we had before. I now have a gear attached to 2 kilograms. Bring the 2 kilograms through the gear, goes as the turn ratio squared, times 0.015 to 1 squared, this 2 kilograms becomes 0.0018 kilogram meter squared. These are in parallel. That adds to the motor's inertia. So the total inertia becomes the motor plus the BattleBot gives me the net inertia. Throw that in the transfer function, and here's the poles. And notice the complex poles disappeared. I now have a pole at minus 3.2. That's kind of why the motor has complex poles. They have to kind of guess what's your application, how much inertia you're going to add to it. In this case, they added quite a bit of inertia, and that shifted the pole quite a bit. But really, the wheel is just a gear. So that kind of wraps up lecture number 16, rotational systems. It looks just like a mass spring system, except my variables are now rotation and torque rather than displacement and force. I've also got gears, and gears look like transformers. That's lecture number 16 for ECE 461 Control Systems.